Tsunami is a very large wave caused by earthquakes, volcanic activity, or landslide. Tsunami comes from the Japanese tsu for harbor, nami for wave, so it's a harbor wave because they are observed in harbors often. A tsunami is produced by an earthquake. Earthquakes can shake the ocean bottom that is moving up and down, and in turn produce waves on the ocean surface. But earthquakes can also produce landslides by destabilizing sediment. Those underwater landslides can produce waves on the surface, and those waves, if they occur very close to shore, can be even more damaging. Landslides usually occur in very shallow water close to coastal areas, so waves produced by landslides move at a very large speed, so they can arrive in coastal regions very, very quickly in a matter of minutes, and therefore there is little warning or no warning at all for populations. So those tsunamis are particularly damaging. Also, the energy produced by the landslide motion is usually concentrated over a small area, whereas earthquakes distribute the energy over a much larger area. So landslide-generated tsunamis can be much more damaging because of that as well. We use a wave tank to conduct experimental research into the physics of tsunamis. We will measure ocean surface elevation at reduced scale, and that information will help us refine numerical models that we are also developing in parallel with the experiments. The wave tank is basically a large pool in which we can make waves, all sorts of waves. We are currently interested in waves generated by underwater landslides. So we've produced a scale model of a landslide looking like a flying saucer type of body sliding down a slope, and that sliding motion produces waves on the surface that look like a tsunami at reduced scale. The wave tank is a physical wave tank where we can make measurements, and the computer model, we call it a numerical wave tank, in which we can numerically simulate on the computer tsunamis and all sorts of different waves. The measurements in the physical wave tank will help us corroborate the predictions of the numerical models. A computer model can help us simulate tsunamis in many situations, so we can actually reproduce historical tsunamis as well as future tsunamis that could happen in an area where the potential for a landslide has been identified. So the numerical prediction could then be used to reduce the risk or mitigate the risk of tsunami hazard for the population. In this case, we actually developed the computer model first and used it to learn more about tsunamis theoretically, and then we developed this experiment and built the equipment in the tank, and we are now gathering data to compare with numerical predictions. A core sample is a sample of ocean bottom sediment that we pick up with a specific equipment looking like a metallic cylinder that we drop from a research vessel onto the ocean bottom. We pick up sediment into that coring equipment and we bring it back to the surface. We can then analyze the core for its properties. We pick up core samples because we want to learn more about the landslides that may have occurred and their type and what have caused them. So the properties of the core sample and the texture of it will tell us information, geological information that we need to know to better identify and classify the landslide and therefore learn more about the tsunami that was produced. So by looking at the ocean bottom and also at the cores, we can identify faults, cracks, and geological features that can tell us the type of landslide that has occurred. For instance, is it a simple translation, which we call a landslide, or is there a rotation of the sediment, which we call a slump, or a combination of both? Those produce different types of tsunamis, and in turn we can simulate those tsunamis in the computer model. Earthquake data is always available because there are many seismographs around the world, about 400 I think, And so we can always go back to those records and find out what kind of earthquake occurred and where. So the combination of earthquake data, core samples, and then sonar imaging of the ocean bottom can help geologists define and understand the types of landslides that have occurred, and then hydrodynamicists such as myself can look at the tsunami itself and predict it better based on the geological data that's gathered. If you look at the seismic activity worldwide, there are earthquakes, many earthquakes every day, every hour. So there are many small landslides associated with those earthquakes. And those landslides and earthquakes together can be creating tsunamis, but most of those tsunamis are very small ones. Only a few of those will be damaging tsunamis. Tsunamis actually occur very, very frequently because there are many landslides occurring during earthquake activity. We think that about in 30% of the cases, landslides are associated with earthquakes. So the computer model we are using has been developed over many, many years, and it is a mathematical representation of the movement of water. And the movement of water can be forced to mimic the movement of a tsunami. So the computer model actually gives us numbers that correspond to the motion, the speed, the elevation of a tsunami.